Example for equation of state is an equation of ideal gas, that is PV is equal to mu RT. A process in which volume of the system is kept constant is called as isochoric process. So isochoric process, work done is zero. The system is undergoing a different thermodynamic process from stage 1 to stage 2, and again it is returning back to its initial state, and such processes we call it as cyclic process. Hello everyone, welcome to session 2 of chapter 12 Thermodynamics. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in the previous session we have studied about the basic terms which are related to thermodynamics. We have even come to know what is thermodynamics, what is thermodynamic system, what is surrounding in thermodynamics, what are the different processes, and also the laws of thermodynamics such as zeroth law and first law and their significances. So in today's session, let us learn more about the concept thermodynamics. So let's begin with state variables and equation of state. What is the meaning of this state variables? Why do we call variable? So variable is something that which is not constant with nature. Correct? So here state variables means we are talking about thermodynamic variable which does not remain same throughout, but it will change. So equilibrium states of a thermodynamic system are described by some variables and they are called as state variables. Example, pressure, volume, temperature and mass. So these are the things which does not remain constant, but it will change, or it will be changing with respect to a thermodynamic system. So we will call it as variables. So the relation between the state variables is called as equation of state. So suppose if we write any relation between these variables, say for example pressure, volume, temperature and so on, such equation is called as equation of state. Example for equation of state is an equation of ideal gas, that is PV is equal to mu RT, where we can observe P is pressure, volume, temperature, and this is the relation between all these variables. So this is one of the equation of state, or we can also call it as state equation. So next we have thermodynamic process. It is so important to understand the different process where thermodynamic system will undergo, and we will call it as thermodynamic processes. So what are these processes? So basically thermodynamic process in which there is a change in thermodynamic variables of a system. So when there is a change in pressure, volume or temperature, etc. So what is the change that we can observe in a process is called as thermodynamic process. There are various thermodynamic processes, one of which is isothermal process. Isothermal process. So iso means same. Thermal means it gives the concept of temperature, which means in isothermal process, the variable which remains constant is temperature. Adiabatic process, where we can observe the heat energy of a system remains constant. Isochoric process is nothing but the volume of the system remains constant and the other variables will change. Next is isobaric process. Isobaric process is pressure constant process, which means in isobaric process the term or the variable that remains constant is pressure. Next is cyclic process. So cyclic process is nothing but process that undergoes various thermodynamic processes and return back to its initial state is called as cyclic process. So let us learn about these processes in detail. So first one is isothermal process. So this process is nothing but the temperature of the system is kept fixed and all the other variables like pressure, volume and etc. will change. So this temperature is fixed throughout the process and this is called as isothermal process. As I said before, iso means same. Thermal means temperature term. So the temperature of the system remains constant throughout and that is denoted by delta T, which is equal to 0. So now equation of state for isothermal process is PV is equal to constant. We know what is equation of state. It's the equation which is relating thermodynamic variables. So PV is equal to constant is the equation of state for isothermal process in which P is nothing but the pressure of gas and V is the volume of gas. So next we are moving on to the conditions of isothermal process. What are the necessary conditions that the system has to satisfy to undergo isothermal process? So the first condition that a system should satisfy is, or it is made up of perfectly conducting material, which means if you consider a container or cylinder, it must be made up of perfectly conducting material, and the system should be compressed or expand very slowly. If the system is undergoing expansion or compression slowly, then the system will get enough time to exchange the heat with the surrounding, so that the temperature inside the system remains constant. Our condition in this isothermal process is to maintain constant temperature. So to maintain constant temperature, the system should be compressed or expand very slowly, so that there is sufficient time for the exchange of heat between the system and surrounding. If the system and the surrounding will get enough time to exchange heat between them, then the temperature in the system remains constant. Example for this is melting of ice and freezing of water. So the next process is adiabatic process. So adiabatic process is nothing but a process in which no heat flows between the system and surrounding. So no heat is exchanged between the system and the surrounding, and we will call it as adiabatic process, which means delta Q remains constant, where Q is nothing but the heat. So it remains constant. Since there is no exchange, it will not vary, so it remains constant. If the heat should not get exchanged with the system and surrounding, or there is no exchange of heat between system and surrounding, then the condition for this is the system must be made up of an insulating condition, which means if you consider a cylinder or anything which is made up of insulating material, then there won't be any exchange of heat between system and surrounding. So the equation of state for adiabatic process in terms of pressure and volume is PV to the power gamma is equal to constant. So again here there is a relation between pressure and volume, which is nothing but the equation of state. So in terms of pressure and volume, we can write PV to the power gamma is equal to constant. In terms of temperature and volume also, we can express this equation of state for adiabatic process. So here in this equation, P is nothing but the pressure of gas, V is nothing but the volume of gas. So what is gamma? Gamma is ratio of specific heats of gases, that is Cp divided by Cv, about which we have already studied in the chapter called thermal properties of matter. So now what are the conditions? I told you already, all walls of the container and piston must be perfectly insulating. Since it is made up of insulating material, there won't be any exchange of heat between the system and the surroundings, so that the heat inside the system must be constant. The system should be compressed and expand suddenly, so that there is no exchange time between the system and surroundings. If the expansion and compression is happening very quickly, the system won't get enough time to exchange its heat with the surrounding, so that inside the system we can maintain a constant heat. And example for this is thermoflask and the bursting of tire. So these two processes will undergo very quick process, and this is an example for adiabatic process. So next we have isochoric process. What is isochoric process? What remains constant in this process? So here the term which remains constant is volume. So a process in which volume of the system is kept constant is called as isochoric process. So isochoric process, work done is zero. How? We know that work done is equal to force into displacement. But force can be expressed in terms of pressure and area, that is P into A into dx. How did we get this? Because we know pressure is equal to force by area, or force is equal to pressure into area. Now area into dx is nothing but a small length, let us consider, and we can write it as P into dV. Here in this process, isochoric process, volume remains constant, that is dV equals 0, and hence this entire term becomes 0, which means work done becomes 0. So the entire heat energy absorbed by the gas is used to change the internal energy, and hence there is no work done on the gas or by the gas. So here the condition for isochoric process is delta V equals 0. Since delta V equals 0, we can say work done is equal to 0. So the first law of thermodynamics becomes delta Q is equal to delta U, which means the whole heat energy absorbed by the system is used to change the internal energy of the system. So next we are moving on to isobaric process. So in this process, the pressure of the system is kept constant. So pressure means delta P is equal to 0. So what's an example for this? The example for isobaric process is cooking in an open vessel, which means we can keep the pressure constant. So next we have a cyclic process. Cyclic process consists of series of changes and which returns the system back to its initial state. Example for cyclic process is a engine working or working of engine or Carnot's engine, which we will be studying in detail in next upcoming slides. So here you can observe the system is undergoing a different thermodynamic process from stage 1 to stage 2, and again it is returning back to its initial state, and such processes we'll call it as cyclic process. So next we have quasi-static process. What is the meaning of quasi-static process? A quasi-static process is an infinitely slow process such that the system remains in thermal and mechanical equilibrium with the surroundings. Throughout the process, if the system remains in thermal and mechanical equilibrium and the entire process is infinitely slow process, then we will call it as quasi-static process. So in a quasi-static process, the pressure and temperature of the environment can differ from those of the system only by very small amount. So there we can observe only a small amount of difference in pressure and temperature in case of quasi-static process. So these are different thermodynamic processes in which a system can undergo, and with the help of all these things we need to derive an expression for work done in isothermal process, work done in adiabatic process. With the help we can also find the efficiency of Carnot engine, and that is how we must know about all these processes prior. So now what are the applications of first law of thermodynamics? We have studied what is first law of thermodynamics in the last session. Now let's move on to its application. So the application of first law of thermodynamics in different thermodynamic process we are going to discuss now. So we know what is the first law of thermodynamics. It is nothing but dq is equal to du plus dw. Now let us see what is the application of this first law of thermodynamics in different thermodynamic processes. So the first one is isothermal process. Now how to apply the first law of thermodynamics in isothermal process? So we all know that it is a process at which the temperature of the system is kept constant. So isothermal means temperature of the system remains constant, and the internal energy of the system remains constant, because the internal energy depends on the motion of molecules. When the temperature remains constant, internal energy obviously remains constant. So therefore the change in internal energy is constant, which means du is equal to 0. Now equation 1 is what? dq is equal to du plus dw is my first law of thermodynamic equation. So when this term becomes 0, we remain with dq is equal to dw. That is, the amount of heat supplied to a system is completely used to do work, because the internal energy of the system remains constant as there is no change in temperature. So next we are moving on to adiabatic process. How to apply the first law of thermodynamics in adiabatic process? So we all know that it's a process in which there is no exchange of heat between the system and the surroundings, and hence heat energy supplied to the system becomes 0. That is, dq becomes 0. So when dq becomes 0, first law of thermodynamics is dq is equal to du plus dw. So when this becomes 0, we get du is equal to minus dw, or dw is equal to minus du. That is, work done by the system is equal to decrease in internal energy. The negative sign symbolizes that the total work done by the system, which will lead to the decrease in internal energy of the system because of the constant heat energy supplied to the system. So next we have isochoric process. It is a process in which the volume of the system is kept constant. As we know that when volume remains constant, the work done by the system remains 0. So I have shown this before only. When dw becomes 0, we get the first law of thermodynamics will become dq is equal to du, because our equation is dq is equal to du plus dw. Since work done is 0, we have dq is equal to du, which means the entire heat energy supplied is utilized to increase the internal energy of the system. So next we are moving on to isobaric process. In isobaric process, as we all know, the pressure is kept constant, and hence change in pressure, that is dP is equal to 0. So what about the equation 1 now? Equation 1 is nothing but the first law of thermodynamics, that is dQ is equal to du plus dW. There is no change in internal energy, work done and heat, and it remains the same. That is, heat supplied to a system is partly utilized to increase the internal energy and the rest of the heat is utilized to do the work by the system. So these are the applications of first law of thermodynamics in different thermodynamic processes. So now let's move on to the limitations of first law of thermodynamics. What are the drawbacks? What are the disadvantages? So first law of thermodynamics just give us the idea of conservation of energy, but it does not tell us about the direction of transfer of heat. We know that the heat flows from a hot body to a cold body. Heat always flows from a body which is of higher temperature to a body which is of lower temperature. But this law does not give any reason as to why heat cannot flow from a cold body to a hot body. It fails to explain this condition, why the heat is not able to pass from a cold body, which is a body which is at lower temperature, to a body which is at higher temperature. We are not able to understand with the help of first law of thermodynamics. So it is one of the limitations from first law of thermodynamics, and it does not tell how much of a given quantity of heat is converted into work. What is the efficiency, or what is the amount of heat it absorbed, and how much of the heat is converted into work, we will not be able to understand with the help of first law of thermodynamics. And it does not tell the conditions under which heat energy is converted into work. What are the necessary conditions that the system must have, or the system must set with? So the condition it will not explain us under what condition the heat energy is converted completely into work. So it fails to explain all these concepts, and these are the major limitations or the drawbacks of first law of thermodynamics. So next we are moving on to an important derivation, exam point of view. This is very important, that is work done in isothermal process. As we all know, isothermal process means the temperature remains constant. That is the first thing we have to understand before we derive anything. So here we are moving on to derive the expression for work done in an isothermal process. So we have considered 1 mole of an ideal gas in a cylinder with conducting walls and piston. We all know the conditions for isothermal process, that the cylinder and the piston are made up of conducting walls. So here we have considered a cylinder, and we have even considered 1 mole of ideal gas, and this cylinder is made up of conducting walls and a piston. Let A is the area of cross section of a piston, and P is the pressure, V is the volume of a gas at temperature T. So these are all our consideration. We have considered 1 mole of ideal gas in a cylinder, and the cylinder is made up of conducting walls and a piston. A be the area of cross section of piston, P be the pressure, V be the volume at temperature T. So when the gas expands by moving a piston by a distance dx, so when the piston moves by a distance of dx, this will move up and the gas starts expanding. So when the gas expands by moving piston by a distance dx, and force acting on a piston, that is F is equal to P into A. So the work done by the gas is given by dW is equal to PA into dx. Why PA into dx? Because work done is equal to force into displacement. So force is nothing but pressure into area. So it can be written as PA into dx. But what is A? A is area into a small length, that is nothing but the volume. So we get dW is equal to P into dV. And this is nothing but the small work done by the gas. Now we have to calculate the total work done. How to find the total work done? The total work done is calculated by integrating the above equation. So if we integrate, means we are combining the small work done to get the total work done. So W is nothing but the total work done. We are integrating small work done, that is dW, to raise the volume from V1 to V2. So the limits are V1 to V2, because initially the gas is at the volume V1. After it expands, it will increase its volume, and that is V2. So limits are V1 and V2, and here dW is nothing but P into dV, where V1 is the initial volume, V2 is the final volume. So now let us integrate. We know that here we have P into dV. So we know that PV is equal to RT, correct? So now from this we can write P is equal to RT divided by V. So let us now substitute the same in the place of P. What do we get? We get limits V1 to V2 RT divided by V. Now R is what? Universal gas constant. T is temperature. Since we are discussing about isothermal process, temperature remains constant. So these two are constant terms. So I'll take this outside and will integrate the remaining thing. So when RT is taken outside, so we get V1 to V2 1 divided by V into dV. So this is what we get after taking R and T outside the integration, since they are constants. Now this is of the form integral of 1 by x dx. We know the standard formula for 1 by x dx, that is log x. So now in the place of x I have 1 by v dv. So this can be written as log of v. So we will get W is equal to RT into log V. The limits are V1 to V2. Now let us substitute the limits, upper limit minus lower limit, to variable V. And we will get W is equal to RT into log of V2 minus log V1. Or we can write it as W is equal to 2.303 into RT log 10 to the base 10 V2 divided by V1. So this is an expression for work done in an isothermal process. So you can either conclude this with a natural log, or you can write it with a proper equation by multiplying 2.303 to represent it with the base 10. So the work done in an isothermal process is given by W is equal to 2.303 RT into log 10 of V2 divided by V1. With the help of this equation, we can even derive the efficiency of Carnot engine, and we will be also solving numericals with the help of these equations. So in the next session, let us derive the expression for work done in an adiabatic process, and we will learn about Carnot seat engine and refrigerator concept and many more. Until then, keep learning all of you. Thank you.